This chart maps out 50 essential algorithms. After spending our first 5 slots covering how to order a list, we are now crossing into a new category: searching. Locating a specific piece of information inside a massive, chaotic pile of raw, unstructured data is one of the oldest computational challenges we face. To solve it, we start with algorithm number 6, linear search. It works exactly the way you would read a phone book if the names weren't alphabetized, starting at the top and checking every single entry in sequence. It is so practical that when computer science pioneers like Donald Knuth set out to rigorously catalog searching methods in the early 1970s, they gave this simple sequential scan its own dedicated study. Complex algorithms demand perfectly organized environments. If you hand them a random data stream arriving in real time, or a linked list where you can't jump straight to the middle, they break down entirely. Linear search requires zero setup. You do not have to pre-sort, and you don't need random access. You point it at the raw information and tell it to run. The logic is straightforward. You set your index to 0, look at the first element, and ask, is this what I am looking for? If not, you move to the next one, repeating until you either find a match or run out of data. This diagram illustrates a scan for the number 22. The algorithm steps left to right and stops instantly at index 4. But if the target is absent, like 91, it compares all 7 elements before returning false. This graphic contrasts linear search against binary search. Linear search works immediately on raw input. Binary search requires a sorted array, meaning you pay a heavy computational tax up front, typically an O of n log n sorting cost. If you only need to search an unsorted dataset exactly once, a linear scan will find the answer and finish its job before a binary search has even finished sorting the first few items. This performance profile shows a worst and average case time complexity of O of n, meaning the search time scales directly with the amount of data. Best case is O of 1 if your target is the very first item. And because it needs no extra memory structures, its space complexity is a highly efficient O of 1. Looking at the Python code, the core engine is just a basic while loop. On every single iteration, it tests if the current element matches the target item. Because the code never makes assumptions about the order of the numbers, you can feed it completely randomized test lists, and it will smoothly parse them without throwing an error. This diagram compares a standard plain loop against Knuth's algorithm Q, known as the sentinel loop. The standard loop does 2 tests per step, checking the value and checking if the search has hit the end of the list. By appending a temporary copy of our target to the very end of the array, acting as a sentinel, we guarantee the loop will eventually find a match. That means we can completely delete the end-of-list safety check, cutting the number of comparisons per step in half. Scanning memory front to back is incredibly cache-friendly for modern CPUs. For small lists, read-once data streams, or linked lists without random access, this sequential walk physically executes faster than jumping around. You abandon this approach when you have a massive, static dataset to search repeatedly. That is the point where paying the one-time sorting tax makes mathematical sense. You can explore the exact code for both the standard and optimized versions of this algorithm in Imran Ahmad's 50 Algorithms Every Programmer Should Know. Linear search is the honest yardstick against which every other method is measured. Once your data is ordered and you are ready to start having your search space, it is time to invoke algorithm number 7.